Okay, let me start. Good morning. So I will go a bit summarizing what we have seen last time about the optimization or training of fully connected neural networks, so the multi-layer perceptron, and then continue the introduction to the convolutional networks from a conceptual point of view. Oh, something is missing here. So going through the concept of scanning networks and distributed input, and then I will briefly mention a couple of famous architectures that kind of revolutionized the field. And then, depending where we are, I will start with the other type of notable architectures. It's called recurrent neural networks, that is actually the basis for transformers and therefore language models. Okay, so last time we saw so every existing neural network architecture will be trained by a variant of this rule. So we start with a set of weights, could be zero, could be random, in all nodes. So this W is a vector, possibly with millions or billions of components. That is what defines the model of the neural network, and then it is trained iteratively by just saying, okay, at any point of iteration I update my weights by looking at the gradient of the loss function with respect to the weights multiplied by some suitable learning rate. So these are the two components, and then I showed a couple of variants of this basic algorithm. So, instead of having just the gradient of the loss function, people use a lot these trend algorithms, in particular the momentum algorithm, in which the actual update in weights comes from a combination of the instantaneous gradient and the kind of average of the previous steps, right? So you have something. So the update itself depends on the previous update, and then it gets a component from the particular step where one is, and just to give an idea, this beta in the linear combination is close to 1 typically. So there is the algorithm is bending towards the previous time steps, so to be robust. And the idea is that this is one way to cure if there are directions, so here would be just a two-dimensional loss function in which the gradient is shallow, and another direction in which the gradient is steep. We favor to increase the step in the direction where it is shallow and decrease where it is steep, because we want to avoid bouncing back and forth. And similar idea is the having an adaptive learning rate, yes. So where we use the root mean square of the gradient. So we take the gradient modulus squared, would be how much the gradient is traveling cumulatively. And this is also in the direction of promoting directions in the optimization where the gradient is shallow, because it will always add up. It's always going down in the same direction, while direction where it is steep, it can possibly flip back and forth, and so the root mean square will not be as large because it doesn't gain enough component in that direction. And so the learning rate is kind of renormalized by the inverse of this root mean square. And the combination of the two would be the adaptive momentum algorithm, nicknamed, so the short name abbreviation is ADAM, that you find very frequently in libraries. The other big kind of technological advance in optimization is when going from a so-called batch update, so where one goes through all the training data and calculate these gradients cumulatively. So before there is an update of the weights, the cumulative change in loss function is collected from all the data in the training set. So this is the batch gradient descent. So one technological advance is to have incremental updates. So we evaluate the change in the gradient for each data point. This cannot be done, or it's not very efficient if you do it without randomly reshuffling the order of the data after each full cycle that is called epoch. So this the combination of random shuffling with incremental update is called stochastic gradient descent. That is basically one of the most common keywords one hears when reading, talking about neural networks. And even better than this incremental update is so-called mini batch. So you do the update every subset of training data, so it's more stable from the optimization point of view. And final point was the regularization ideas. So the general idea of a regularization in machine learning is that the loss function is a combination of penalty on the error related to the error. So the model minus the ground truth gives some one term in the loss function. So it could be the L2, so the squared, the Euclidean distance squared, or the integral over all the data points, or the sum if you have finite set, as one usually does. But most importantly, so the regularization is some kind of penalty on the size, complexity of the weights themselves, right? So this is general expression for regularization in machine learning. That is, how to say, a necessary ingredient, especially when you're doing say linear regression, polynomial linear regression, and these kind of things. The regularization is what made the algorithm actual machine learning. Otherwise, it would be just some kind of fitting without too much of care about the stability of the model. It turns out, so there are schemes where the weights themselves in the neural networks are regularized, typically with an L2 norm. But one has to consider that the depth of a deep neural network is a regularization. One can show, also can prove bounds for this regularization, so that each layer is smearing out the input by construction, essentially. So there is a regularization that comes naturally from depth. And actually, that this is one of the main reasons why we have deep neural networks. So one can ask, given a certain number of nodes that would relate to a certain number of weights, so this would be the size of our neural network that is related essentially to the computational cost of training it, and then also evaluating it, because you still have to do all the feed forward every time you want to evaluate. So what is the advantage of arranging the same number of nodes in layers versus in one shallow but very large layer? What is the advantage, given that one can prove that with one hidden layer one can already get a universal classifier or regressor? So one can formally prove, or strongly prove that you with the number of nodes in one shallow layer that goes to infinite, one can approximate any possible given function. The point is that one can show that if you arrange in layers, you need fewer overall nodes. This is much involved to prove. I had at some point, previous time I gave the course, proof when you have a logical operator. So if you want to do the whole kind of AND or kind of function for any size of input, you can sort of show pretty easily that you need a kind of exponential number of nodes with a number of gates, while if you do it in layers, you just need a linear number of nodes. But then I thought that, I mean, it takes half an hour and you don't gain much more than what I am saying, and that's specifically to logical kind of networks that are not very interesting for us. I mean, they are for computer science. And the proof for a regressor is very involved, so I never would like to do it in a lecture. So, but in general, there is this concept that for the same accuracy, I would say, you would have a kind of exponentially smaller number of overall nodes in a deep network than in the same network arranged in one in one single hidden layer. So it's not a negligible advantage to do deep networks. So then the other dropouts kind of the other regularization idea, very strong idea that you have in network, not very easy to implement in other model classes, is the dropout idea, where when we do the training, we randomly, so for each epoch, we switch off some nodes. That means we set all the weights going to that node to 0. So even at some point you're doing the training, so you have acquired some knowledge that these weights are different from 0. You set them to 0 and you let the network continue learning using all the other nodes. And then you cycle over this with the, again, random selection. So this has the benefit that so kind of descriptive benefit that one does not specialize neurons to specific part of the parameter space. So one can show that if you don't use this approach, there will be, so if you track which neurons are more active for a certain kind of input, the network will try to specialize, and this is typically a bad sign. And the other thing is that so it is very related, but the fact that we are doing in fact a learning of an ensemble of networks, because one can see switching randomly off and on nodes to one is sampling 2 to the power n network. So this all the possible subset of networks that have any combination of switched on and off nodes. And this is not just impressive to write. One can show that the benefit converges to training this astronomical number of network, while one is training only one network. So from the algorithmical point of view. And then the other kind of regularization approach or idea is the so-called early stopping that you also see very often in literature. And if you know what you're doing, do it. So the idea is that with the number of epochs, so that the training error will go down by definition. So it will start large because at the beginning the network is randomly or zero kind of weight. So it will have a large loss function, and it will go down because you are optimizing it. The training error by definition. I mean, if it doesn't go down, something is going wrong in your optimization algorithm. But at some point, the validation error, so the error on data that are not used, at least in that particular epoch for training, it will go up, and then so one stops when the network starts going up. And here the dotted line refers to the fact that sometimes you have a secondary minimum or actually more minima. So depending on which type of problem and how large would be the error here, that might not be very nice. So the first time you see that validation error going up, it could be that then it goes down again. So it is useful to monitor this learning curve. Actually, that this plot here, just to stay with the nomenclature, is called learning curve. So if you read learning curve in literature, a referee is saying, what about the learning curve? They mean validation error as a function of number of epochs. And this is more or less the summary of the ideas that are behind the optimization of networks. There are then specific concepts related to the different architectures, but honestly, I'm not sure I want to go more in detail. So for convolutional network, there are other kind of tricks in some sense, and so on and so forth. But I want to rather give an overview than go into too much technical details. So this is about optimization, and then we started looking into convolutional networks, where the idea is to do pattern recognition, and one can think of, so like the original motivation when people started looking into convolutional network back in the 90s, actually, before the kind of official renaissance of deep learning. I don't know if I already said that. So basically, neural networks have been existing since the say the 60s in some sense, or I mean in many senses, like a network of perceptrons. So the perceptron system from the late 50s, and then the next obvious idea, at least if you you are in the field, is to make a network of perceptrons. And then, okay, there was not enough computer power, and the algorithm were not mature, and then people had hard time training the networks, and so they stayed always a little bit of a fringe kind of application, and other machine learning methods were much more, how to say, common. Since apparently classification is one of the most important kind of problem that you encounter, probably outside, say, physics and engineering, so in many applications. So the field was dominated by support vector machine for classification, proved to have a very robust algorithm, very stable solution with some tricks and so on. And so, let's say, especially in the 90s, the neural networks were really kind of marginal or marginalized, and people still doing research in neural network were kind of frowned upon, and to the point that at some point when you had a paper with neural network for conferences, machine learning conferences, it was kind of rejected by definition. At least this is what the people that then were part of the Renaissance, so LeCun and Yoshua Bengio, still tell these days. So at some point they decided to rebrand completely the field and call it deep learning. So this is a story that they tell around in podcasts, but I think also in the books. So the interesting thing is that we have research on convolutional networks already in the 90s, as I will show more or less towards the end of this lecture. But definitely they became very important in the last 15 years, I would say now. Not 10, but a bit more than that. So the general idea is to do pattern recognition, right? So we know that a multilayer perceptron can model essentially everything. It is a universal approximator, but at the price of having an unspecified number of possible connection among neurons, therefore weights to train. And in computer science you have always the kind of trade-off or very subtle balancing, which you say, okay, this number is too big. There's still maybe billions, like now you do with transformers, but billions is feasible maybe, but 10 to the power 16 it is not. So you want to still keep the numbers in. And so convolutional network is one answer to this trade-off. And specifically, people were interested in finding speech patterns. So what you see here is called spectrogram. So one is recording kind of the sound, some speech. So as a function of time, you would have spectra and frequency, right? So each column here would be a frequency spectrum that is recorded. And then a certain pattern in the frequency spectrum would be a certain word. So somebody's uttering welcome, and this would be what appear in the spectrogram. So the trained eye would be able to recognize where this utterance appear in the spectrogram. And so the key point here is that you have something that is distributed in time, so it's not just looking for something that happens in one specific time step, but there is some kind of thing that pattern that is across time, but it has a certain number of dimensions. So here it has many numbers as your frequency spectrum, at least the beginning of the frequency spectrum. So the input would have a dimension of size of the frequency spectrum times the interval in time that you need to sample in order to recognize that pattern. And if it was an image, so here I drew something very agnostic, meaning that it could be really a picture of stars, and you want to find if there are stars in that picture, or it could be a pattern on a microscopy image, equally interesting, so that there is something you're looking for, some adsorbate, and you have a certain pattern that you can recognize. And the idea is that so you have an overall input image, and you're looking for something that exists in a subset of that image. And so the initial step, besides, just giving the whole image and just saying, okay, yes, in the training here there is at least one star or one instance of welcome or no. The next smart step is to say, well, let's say that I have a network that looks only at a specific subset of the image, say some interval, and then I conceptually move the network in time. So I give to the same network another input in the next window, and so on and so forth. And then I train the overall set of networks to say, okay, if there is at least one of this network that has seen the signal, so that gives one as an output, so the probability that I see the signal becomes one. And then I have a OR kind of gate that essentially is realized by a softmax. I get overall positive signal, training signal, and then I train the network in this way. So the softmax is doing the same as OR, because okay, you just needed one of these as a strong, close to one output in order to get a one coming out of here. And so with respect to having a network that digests the overall signal at once, is that we have much fewer neurons dedicated to understanding only a subset of the signal, and then there are no connections. So this is the drawing is somewhat accurate in the sense that there is no connection between first instance and second instance of the network, and so on and so forth. And equally important is that these subnetworks are identical, so the weights on each connection is the same, independent of the location. So all this together gives a scanning shared parameter network that, if you zoom into the overall weight matrix, would be block diagonal instead of dense, right? So if you just have a layer here and everything is connected with the next layer, you would have a weight matrix that would be fully, so it would be dense. Everything is potentially different from zero, and while here you force that only a subset is different from zero, and even well, no, equally important is that they are replica of each other. So you are training by far fewer parameters. Of course, one can say, yeah, okay, even if you have the fully connected one, a solution would be this scanning network, but you would need the network to find a solution by itself. That could be some cases prohibitive. So in a way, not in a way, this is a regularization, right? So I like always to see this kind of architectural ideas as regularization, because essentially we are imposing that in the all possible weights, most of them here are zeros, and they are cleverly selected by construction. Okay, and then the next kind of realization is that, so if we write down in pseudocode this kind of shared parameter scanning network, we would have a loop over times. So we are scanning the signal, right? So we have a loop over the time, and then for each time, so you see you have a window. Well, no, this is actually written that it goes in one step. So the window is here. So you pass to the a multi-layer perceptron an input that goes between the time t and time t plus k. So this is your size of the window, right? So this is saying that you give the input to this sub-network here. And then at the end, you do the softmax of all the inputs at all times. So y as a function of t, time 1 until the last time, and then if at least one is different from zero, you get a positive signal. Incidentally, then even if you have two times, the signal is still 1. So the network is equally happy if you see the signal many number of times as much as 1. So it doesn't make a difference. So because you are just asking if there is a certain pattern in the signal at all. And exploding a little bit the multilayer perceptron part. So you have a loop over layers. So here would be layer 1, layer 2, and layer 3 in this cartoon. And for each layer you go over all the nodes in the layer, and okay, for the first layer the output of the layer is actually the input, but otherwise you do the affine transformation, so initialize with the bias and then multiply by the weights. So the input of the previous layer multiplied by the weights give these z's that are kind of universal name of the variable after the affine transformation, and then the y's are the activation of the z's. So this is what happens in any multilayer perceptron, and then you do the softmax. And then the next interesting step in order to approach the actual convolutional network is that we realize that there is no operation happening between the loop over time and over a layer, so we can invert them. So we do a loop over layer and then a loop over time. That in practice means that basically the whole signal is given to the first layer, and then we so in steps we give it, and then we propagate to the next layers, right? So here where we arrived last time. And now the next thing to look into is distributing the input over layer. And to do that, we go to the new whiteboard. So to talk about distribution, so I sketched this network architecture to show the following. So let's say that we have this input image in which might be the pattern, and then we have a layer here. So each circle is a node or neuron, and what a neuron does is that it accepts say a portion of the image, right? So this would be a bitmap, and then the one neuron would accept a portion of the image, and then after the affine transformation and the activation, it will output a signal, and the reason why I did a kind of array of plots here, of dots here, is that then one has to imagine scanning. So like then we would have another position where the neuron gets input, and it would map in another output. So you can arrange these outputs in a so-called map. So this is what the first neuron is doing in the first layer, is mapping the original image in a map of that image. So you would have some kind of output. Then you would have another neuron that would do another kind of mapping, and it would output in a map as well, and so on and so forth for all the other neurons. So each neuron would filter the image and output a map. Now the next layer, the way a scanning network is working. So if you consider the whole block here as a multilayer perceptron, so the multilayer perceptron now does not need to know at all that there was a scanning of the input. So there is just something that the previous layer has been outputting, and so say this neuron in the second layer would make a linear combination of the output, or an affine transformation of the output in the first layer, and construct another map, right? So it would be top left for all the neurons in the previous layer into the top left of the output map, and the same would do the second neuron, right? So same. Oops. And this would output here, and this would continue, right? So probably this one. The next layer would take this and output here, and then when the input is scanned, it will construct maps at different layers, right? So the point here is that only the first layer is doing actually the scanning of the initial image, and then the next layers will just take a linear combination of the output of the first layer, or of the previous layer. So the key point is the kind of unbalance between having a first layer going through a certain window in the input, while all the other layers take only one specific output of the previous layer. So the kind of obvious extension would be to say, well, why my second layer, okay, what color could use, cannot take actually a larger window from the previous layer and propagate that to the next layers. And this is exactly what the distribution does in the, sorry, I copy again the clean oops. So this would be non-distributed. And the distributed counterpart would be, take the input, give it to the first layer, it will output always one single signal, but then the next layer does this. Well, of course, does this always. Take a linear combination, but of a larger portion of the output of the previous layer. So this is where the distribution comes in, and this can be propagated through layers. So the advantage of such operation is that so effectively the second layer now, let's say, would be looking at a larger window in the previous layer, or the other way around, we can achieve the same window size by having the first layer looking at the smaller region. And this is the so-called hierarchical feature construction. That happens in a convolutional network in this sense. So the say the first layer will kind of after the training sort of learn to recognize certain small patterns, right? So maybe now I should give, yeah, okay, you can follow that. Some kind of finely detailed patterns, still few pixels, so it's not just noise of every single pixel, but somewhat smaller. So it will be trained to recognize if certain feature on a short scale exists. And then the second layer will understand if a certain larger feature exists, and so on and so forth, propagating through the layers. So this is sometimes you see when seeing this explanation for actual images that so they say the first layer would recognize some kind of horizontal, vertical, diagonal lines, and then they will start building together in order to make a certain humanly describable feature like an eye or a whisker or whatever. And the sketch here should kind of hint in that direction, right? So the the scanning network would do something similar, but basically it can only find the whole pattern or not, because then everything that is propagated beyond is related to the initial window. Everything else is just looking at the first at the output of the previous layer. While here it is a combination of outputs from different positions of the scanning window from the previous layer. So this is how you build this hierarchical map of the initial image. Okay, so what else I want to say here? Yes, yeah, this is a bit. And now let me give a kind of approximate description on how, also in this case, we dramatically reduce of the number of, so with the distributed kind of idea, we dramatically reduce the number of neurons and connections. So to do that, I go back. Yes.
Yeah, so a few questions. First thing, when I look at these graphs there, what are we searching for there? So is it kind of an object detection that we search different colors on a picture, for example?
Well, no, this would be more a shape that we are looking for. I mean, we could have colors. If we have, so we decompose the signal in its color, so we would have a different neurons for each color. This would be a possibility. Why do you have more than one neuron in each layer?
Different properties.
Or different properties of any kind, right? And then the idea is that overall, if that property pattern is present, it will propagate through the network, and in the final layer that I have not yet fully specified, you have like a 1 at the end. There is something there, right? Okay. And then all the weights are adjusted in order to kind of make this happen. Okay. Right.
And one more question about that. How would we realize something like these first layers just by adjusting the input for each part? So, for example, when the black, so the first one is one sub-network, or the red one is one sub-network, we kind of split the input and give each of them a different input. And this is how we realize these mappings, or different mappings?
The mappings, so this is, okay, the mapping is what the network is doing. What we give as an input is exactly what I have in the pseudocode here. So basically we start giving, so for each layer, for each time, and for each neuron, we give the input signal that will be the transformation, and so on and so forth. So in practice, the image is partitioned, and then each sub-image is given as an input, and this is exactly what it is here. So this is the sub-image. that generates an output, transformation, blah blah, and everything is stored in these Ys and cycled overall, and then you get the final big Y that is the output, and this is the one that goes in the loss function, and the backpropagation will adjust the weights. Yeah, does it answer your question?
Yeah.
Okay.
So it's like when we have just the input vector, so we split it at some points that.
Yeah. Yes. With one little difference is that I didn't mention, but the windows can overlap. You don't have anything saying so. The technical term is stride. So you define actually typically in your convolutional network what is the size, that is this k, and then you have another parameter that is the stride. So you could have that the next window is actually somewhere. Oops. Here. So with as much overlap as you want with the previous one. So it's not really a partitioning, it's really like that you split the image in all these sub images. Yeah.
Okay, but physically separate before going into the network.
Absolutely, yes. Yeah.
Excuse me, madam. I thought I kind of understand it, but perhaps I don't. Because now what are the, so I understand the first step by the scanning, it's kind of clear.
Mm-hmm.
But then what are those, or why are there those, in your case, 4 different neurons? Because for me then each of those still works with a matrix.
Yes.
Or does it not?
Yeah. Yeah, each neuron is applying a filter to the image. Okay, I will arrive at that when I write exactly what each neuron is doing. But so basically, there will be weights. Absolutely. So you take. So here, imagine that the input window is pixelated, and you take a fine transformation of the overall input matrix, the bitmap. And then you have the activation. And that will give a number between 0 and 1. And this is what enter here, top left. The question is, what is every different neuron doing? The same thing, except that you don't ask that the weights are the same. So what will happen in the training is that each neuron, in some sense, will specialize in understanding some sub-pattern, so that the overall network is doing the learning. So this is the part that I always find confusing when reading about whiskers and whatever. So we don't give this information to the network. The network is kind of understanding, yes, that in order to give the overall performance, some neurons have to do this kind of filtering, and the other neurons do the another filtering, and not all of them, or most of them, we will never understand what they are because they might be quite delocalized. Yeah, so that's a very good point, because I had difficulties in understanding at the beginning, because it is always playing like we design the filters. Like here you can say, okay, now I do a Gaussian blurring, or I do a kind of another blurring that finds the horizontal or diagonal, or I mean, you can design these kind of filters pretty easily, but of course we don't do that. We just give the network the training of the network to learn it by itself, and it works. That's but if you don't do this kind of partitioning of the network and the connection, it may never find. It will find another solution that it is completely delocalized, let's say, and with the cost of a huge number of extra neurons that you need to do the same task. Yeah, probably the next step tries also to quantify how you reduce the number of neurons. So basically, let me see, if we have so now oops, I change a little bit the graphical representation. That is a little bit useful for the next. So these are now layers. The neurons are vertical because it's a little bit easier. If I want to, so I'm scanning a time signal, and I have a scanning network that accepts a kind of signal of length 8 time step. The number 8 is useful because it's 2 to the power 3, as you will see in the following. So let's say that we have a network that will scan. Will accept the input from 8 different time steps, and then it will scan. So it has to have enough. So it has a certain number of neurons in each layer, and then the overall number of weights that we need for such networks would be 8 times the dimension of the input. So remember that each time step, this can be a vector in frequency or whatever. So the dimension of the input times the number of neurons in the first layer, and then we would have neuron in the first layer times the neurons in the first layer, so the all-to-all connection between the first and the second, and then N2 and 3. Yes, so this would be the overall number of weights that we would need for this network. Now let's say that we do the distribution, so that means that we have very similar N1, but now we have something like this. So these are different, N1, N2, and N3, possibly different. So what I'm doing with this sketch is to say now the first layer accepts only an interval of 2, but the second layer is accepting an interval of 4 from the first layer. So effectively, we are passing the same amount of information to the second layer, and then the second layer to the third layer, right? So we are just arranging differently how the first 2 layers are connected. So this, this distributed architecture would have now 2dn 1 plus 4. Okay, plus the same, and 2 and 3. Now the catch is that so the number of neurons that I need in the first layer in this way is 1/4 of the one that I need in this one. So if I rewrite as the number of neurons that I have in the other one, it would be A times D times 4 the N1 plus 4 the N1 prime plus the same here. Well, everything primed, but they are the same. So basically it's this one that you need fewer, because now the first layer accepts a much smaller window, and then it propagates to the next layer. And then so if we compare these two, we have gone, so now everything is the same, N1 and N2 and are the primed one. So here we have 32, and here you have 2, and here you have the same, 4 and 4. So you see that this is a quadratic, essentially, the scale down. So if you reduce by 4, the the size of the input windows, and then you just group the first layer with the same size 4. The overall gain in number of neurons is 4 squared, so it's 16. You go from and the same would be if we do the next. What was that? Yeah, we need to do the first 2 and again 2 to the third layer. So overall, still an overall Windows of 8, but we have propagated 2, 2, and again 2, and so we have 2D, how did I use that to be the second, plus 2 and 1 and 2, plus 2 and 2 and 3, and yeah, actually I should have rather, well, okay. If I go back to the original network, it would be 8D4 and 2 plus 4 and 2, the factor 2 here. So if I make it in the original representation, you have now you go from 2 to 32 here, and from 2 to 8 here. So again, you have this quadratic scale down. If I distribute more and more, and actually I need even fewer neurons if I do the distribution. So this is a kind of single case explanation in which it gets even more complicated with all the indexes and so on when I go to a two-dimensional image, but you have a similar kind of concept that we if we compare the network that does the scanning at the first layer to the distributed one, we reduce the number of, so it's quadratic for each layer. So you reduce really with the power law and very fast. Right. So now it's the time to show a bit of a summary of what the network is doing in each of these convolutional layer. So could be the input or could be any layer. What you get is an input image or map from the these Y's are the output of the previous layer. That for the first layer is the actual input, and then each neuron, so this would be the representation of each layer. Each neuron is actually represented by a filter, because you have that you have this filter that goes over the previous map. So this would be a 3 by 3, so it goes over 3 by 3 here, and it would do the convolution would mean this time this plus this time this, and so on and so forth, to get the Z of that layer position 1. And then it goes over all the previous inputs and over all the neurons in that layer. So, in summary, mathematically you would have that affine transformation. The index here is the layer. This is the index of the neuron, and x and y is the position. So this would be for a two-dimensional kind of convolutional network. And then you go over the outputs of the previous layer. Again, m is the index of the neurons of the previous layer, and x and y are the positions, and you are scanning. So then you sum over x plus y, j plus y, and you have for each of them a specific weight. So that you have a weight that connects the neuron in this layer, so in the previous layer, the neuron in this layer, n, m and n, and each of them is actually a matrix. That here would be a 3 by 3 matrix. This is why it's called a filter. So you have a kind of four-dimensional object here, and then you have an offset bias. So this is exactly what it is doing, and this operation, because of this part here, is a convolution, right? So it's you can say it's a convolution in general would be integral of some function of t and some function. Well, mathematically and physically normally there is a minus, but it could be also plus. It doesn't really matter here, right? And then you integrate over t. So right, your convolution would be, you have a function f, and your g, for example, is a Gaussian. And what you're doing here, you are doing, so g typically has a finite support as the filter here, and then you're doing the integral of the product of these two. So basically, if this was a Gaussian, you would get as outcome of the integral at certain time tau the kind of smeared value of the function centered at a certain time t, right? So this is what it is called the convolution in mathematics and physics, and the convolutional network is doing essentially the same. So each neuron is taking the convolution of this filter with the input of the previous layer. Right. So this is the kind of justification why this is called convolutional neural network. Oh, this particular part of the network is called convolutional layer. And then in order to make a convolutional neural network, we need convolutional layers and a couple of other things. So people add, and again, you might have heard about pooling layers. That come from where do I have something here? Well, yeah, okay, we could use this one. So basically, the image, the pattern that you're looking for could be a little bit at the border of different pixels. So there could be, so imagine a microscopy image. There is some kind of jittering of the apparatus itself. So something can move in the image, or in any case, you might not have exactly the feature aligned with the input representation, so your bitmap. And so people realize that you need to have something that does max pooling. I mean, you can do anything, but the typical are max and mean pooling. So that is something like this. So you have any layer, some kind of map that may look like this one, and then you define the size of the pooling, that, for example, is a 2 by 2. And then you look for where is the maximum in this 2 by 2 array located, and so you transform into a layer that is now, well, it was 4 by 4, but so each 2 by 2 will be mapped into one. Sorry, this is not what this does. This does something different. That is again a 4 by 4. But all the pixels, so the outputs of this of each 2 by 2 gets the maximum or the minimum. The important thing is that they get all the same value. So it could be the maximum out of these 4 or the average value of these 4. So there is some kind of smearing or in any case it is always a smearing, because in any case it distributes a value over 4 pixels from the previous map. The mean would act more or less the same. You could have more complicated things. You could have a whole neural network between this and that is learned. So you have instances in which you are just learning a function, right? Max, mean, or another function that goes from here to there. The only prescription is that you give exactly the same value to all the pixels in the output. And then since these kind of operations kind of tend to reduce the size of the image, you have an upscaling layer. So one that says, okay, now I go from say a 2 by 2 to a 3 by 3, for example, in order to kind of scale up the image, again with some kind of rule on how to map neurons to neurons. So these layers are typically not learned. Pooling and upscaling, there is just a rule to go from one to the other. Everything goes in the convolutional layers that can be and will be learned. In some textbooks you still find that there is a loose justification that so people in the maybe up to the 90s, when looking at the neural cortex of animals, when looking at images, they kind of realized that there were this kind of alternation of layers that do some kind of so they labeled it convolution because it was something that was changing in time. So there was some learning feature happening, process, and there were other layers of neurons that seem to be fixed, so they do always the same thing, and then there was kind of conceptualized as, okay, it's doing an operation that is embedded in the architecture itself. As you can imagine, this was kind of research at some point stopped because, of course, it's not very mild on the animals at all. So, and in the end of the day, there was not much understanding going on. It was just a justification of things happening. Right. So when we combine this kind of type of layers, we have a convolutional network. And now time to kind of show a little bit of Hall of Fame. So the first, so the breakthrough was in 1998, I think. The famous, did they put that there? 1998 was the LeNet, because the guy behind is called Jan LeCun, is still one of the most important researchers in neural networks. And then so you have LeNet, so addressing the NIST. So these are handwritten digits between 0 and 9. I think you might have heard or seen already. So there is a database from the NIST Institute in US that they had all these handwritten digits. The purpose was to kind of try to automatize the understanding of zip codes on letters, and so basically people had been doing a lot with networks with some success, but the group of LeCun came with these 3 layers. Well, it was like I think, yeah. It was a 3 layers ConvNet. So already with this idea that you have a convolutional layer, max pooling. So it was all these kind of things, convolutional again, and so on. And then you have the final layer. Yeah, I didn't ever mention this thing. I should have. So let me go to the general plot here. So after all the convolutions happen, what one does for the final decision is to flatten the last map, right? So you can still arrange the map in an array, but what actually happens is that each output is taken singularly, and then some multi-layer perceptron is built from this input, right? So independent, basically, you lose the spatial information here. You just give all these outputs here to multi-layer perceptron that is trained separately. No, sorry, not separately, concurrently, but with a different architecture. So you always have this kind of final multi-layer perceptron, and it was another 3-layer perceptron, multi-layer perceptron. This was the general ConvNet. The important thing could be, yes, you have 60K parameters, weights that were trained, and in the late 90s, that was the right number to get something that completely outperformed every other architecture, right? So the genius there was to design this architecture so that you had only 60,000 parameters, and then it was fantastic performance on the MNIST. And to get the next, so actually, there was no conceptual advance until the famous AlexNet. So the AlexNet was another convolutional network exactly as this one, acting on ImageNet. So ImageNet is a database of millions. So at that time it was 1.2 millions image, so the one that he used. And so these were just pictures labeled in 100 classes. Sorry, 1,000 classes. So there were 1,000 possible labels of these images, and this AlexNet was trained to label them automatically, and that was a kind of a prize winner network, but essentially with the same concept and ideas as for the network of 14, 15 years before, except that now we had 16 millions parameters, right? So at that point we had, I think Microsoft had the computer power to train such network. Conceptual change was in 2015 with another network that you might hear and could be useful also for microscopy images and so on. It's called ResNet. So the new idea here is that we have a convolutional layer, that gives some kind of transformation of the input x, but at the same time you so the next layer would have a combination of the output of the previous layer and the new transformation. So the idea here is that you kind of propagate the initial signal across layers. So this plus is actually an union. So basically that layer takes the map that comes from the previous layer and the original image. So they are just kind of a two-dimensional stack of the two images. So it will, the next layer will deal with the original and the transformed one at each step. And this kind of was shown to reinforce the input signal. I don't have particular parameters, but soon afterwards, so everything gets kind of always faster and faster, right? Takes 15 years to get to some kind of advance, and then you have a new concept, and the next year there is another one that is the kind of logical improvement. So basically each layer propagates to the next layer. So let me see if I can. So this one gets to the next one. So this would be a convolutional layer, and then you have that this output propagates to the next, and this output propagates to all the next, and so on and so forth. So that means that people says, okay, if you give to each layer information from the previous layer, you reinforce the outcome. So this is called DenseNet, and it was another breakthrough. Then they say convolutional networks kept on being improved and updated, but then a couple of years later, actually the original paper is from 2015, transformers arrived, and then the attention shift, okay, pun non intended, and the attention shifts to the transformers and their updates. Okay, so this is what I want to say on convolution network. Let me just introduce the next big block of network architecture that come from say also the convolutional network were motivated by signal analysis, so people wanted to find patterns in signals, and the residual network come from the say the models for analyzing time series. So we have the so-called finite response systems that have a very long history in engineering in particular. So the idea is that one wants to model an output of some device or some process as a function of an input at that time step and it input at previous time steps. Right? So this kind of modeling, there is a whole class of finite response systems, as much older than the neural networks, and yeah, indeed they appear in every branch of engineering, from nuclear engineering to model the radioactive decays and neutron fluxes, to say hydraulic. So every time you want to model a system of pipes or lakes with rivers, this kind of model pop up over and over. So you have the final response system. The idea is that you have a certain input at time t, and you keep track of the input at previous discrete time steps, and you want a model that gives an output that is predictive. And a neural network actually architecture is useful for this kind of models. So basically, one can say, okay, I have a neural network that outputs some kind of prediction, and then I have a time series here. So I have the x time -1, -2, say -3. So you basically give as an input to the network a certain set of inputs, and you just keep giving it. So the idea is similar to the scanning network that I described before. So the sketch here is the same network that gets different inputs. So the inner machinery here is the same in time, and we are just training the network to give certain output given the previous input, and so on and so forth. So we can train such network. Obviously, the important point here is n, not much, -n. So how many? So we have a kind of fixed length interval that we are giving to the model. So we need to justify why that particular interval in time is important or sufficient, more importantly. So if one cannot commit to a specific time interval, we have the infinite response systems that very elegantly, I would say, they just are formally described in this way. So basically now you have that the oops, shouldn't have pressed the button. Oh, nice. That the output at times t is now a function of the input at times t and the output at previous time. So this is where the recursion of the recurrence. Oh, residual. Okay, completely. Sorry. These are recurrent networks. Is that where the recursion starts appearing? So let me. And from a point of view of sketching a neural network architecture, again, this doesn't need to be a neural network, but we can easily map this into a neural network. That is, so we have a block, some kind of original input. This would be a parameter to be learned. And then the input at times t plus 1, and so on. No. Something like this. So basically, you have a network that accepts as inputs some combination, could be concatenation of the input at that particular time step and the output at the previous time step. And this is the kind of starting point for recurrent networks. It turns out that it is better analyzed with the so-called state system model. So that the update is basically split into two parts. We define a state function it is a function of that step and the state function at the previous step, and then we have a function that goes to the actual output. In this way, we can decouple the information that it is given to the network at the next, so the model at the next step, and the actual output. So typically, the output is a subset of the state. And so we have schematically that you have state 0, state -1, state 1, and okay, very similar, but now it's a bit cleaner that we propagate in this way. Right. So basically, we have a state vector h that it is propagate, so it's passed to the next instance of the network together with the new input, and this gives the output. And again, so each of these squares is actually our neural network that has a lot of weight, and this is essentially, yeah. I stop here, and next time I will restart here by writing how the network update looks like, and then from there start complicating a little bit the model until we arrive at transformers, essentially. Yeah. So, but the starting point is modeling time series with this kind of state function representation or modeling, and the time series can be sort of literal in the sense that you have an observable in time. Typical example in textbook is a stock market, but so anything that really is as physical sense could be modeled in this way. But it could be something that has just an ordering by itself, so language. So it could be modeled by this recurrent network, or actually a bit more complicated. There are instances of natural language processing that uses kind of simple recurrent networks. Yeah, okay, so I stop here. Thank you.